I'm Suresh, as you can see. That's my email address. So I'll be talking about this thing called the Hilbert's 10th problem. So just in case you need some reference, I am basing this on a book which is titled Hilbert's 10th problem. This book is by M. Ramamurthy and Brandon Forden. So that's an American Mathematical Society publication, in case you want to search. I'm also basing it on an article by Martin Davis. The book is about 2017 or whatever, very recent. The article is 1973. American Mathematical Monthly. Yeah. So just in case you need some references, you can. The article is quite readable. There are lots of details that you might have to plow through, but you don't need any advanced math for it. If I can understand all this, you can also understand it. So think about it that way. Okay, so let's begin. How many of you have heard of Hilbert? Oh, very nice, a lot of you. So David Hilbert, so in preparation for this talk, I also wrote down, how do I go to the next page? Huh? Right. Where is the mouse? Scroll. Okay, good. Okay. I'm having difficulty with this, but it's okay. So David Hilbert was a mathematician who lived from 1862 to 1943. He was one of the most influential mathematicians of his time. In 1900, he gave a famous lecture at ICM. How many of you have heard of ICM? International Congress of Mathematicians, okay, in which he listed out 23 problems. Don't ask me what all the 23 are, I don't know. I only know two, okay, one of which is Hilbert's 10th problem, okay. So he listed out these problems which were open during his time, and he said that trying to work on this problem and resolve these problems would lead to significant advances in mathematics, okay? And it has actually turned out to be true. Many of these problems have even created new areas and so on. In fact, several of the problems that he has listed is very closely related to the beginnings of computer science, okay? And some of the problems are explicitly computer science-ish, if you think, including the 10th problem, which I can describe to you now. Yeah, I figured out how to scroll it. Okay. So, what is Hilbert's 10th problem? You have to go back to Diophantus, who was a Greek mathematician in the 2nd or 3rd century of the Common Era. So, he studied equations of these forms, polynomials with several variables, right? So, I don't know. So, here is an example. You can even think of it as systems of equations. Here is an example. Okay, so you study a system like this and ask, are there values that you can plug in for the variables w, x, y, z such that all these equations are satisfied? Okay, so do you have any quick means of solving this? I don't have, so I'll tell you. Okay, so you can actually verify that this is a solution. W equals 1, X equal to 1, Y equals 2, Z equals 4. Okay, that's the solution. Importantly, you want to ask for solutions in integers. Okay, so you have a bunch of equations, polynomial equations with with integer coefficients, and you are asking for, are there integer values that I can plug in for the variables such that all these equations are simultaneously satisfied. Okay, so you can verify that this is a solution for this. So quick question that I want to ask: given a solution and given these equations, how much time does it take to verify? It's polynomial time, no matter what. So is this problem in NP? What is the problem? I haven't told you it. The problem is, given a system of equations like this, are there values that you can plug into the variables such that all the equations are satisfied? Okay. So you just told me that if I give you a solution, you can always check whether it is a solution in polynomial time. So why is this not in NP? This whole problem? Because if you recall in the last lecture, NP is all problems that are efficiently verifiable. Yeah. So yes, it is efficiently verifiable once you give a solution, but the solution could be very, very large. Okay. So it so happens that for this system of equations, there is a very short solution, but you might have these numbers, there are no bounds to these numbers. You might satisfy some of these equations only when, W is 1 million or whatever. So you don't know a priori how large the solutions are. So you cannot have an algorithm which just goes through all numbers and checks whether one by one whether it is. Yeah, so it won't be considered NP because the solutions could be very large. Anyway, so that's just a side remark. I'll ask you another question. Suppose you consider the same system of equations but mildly modified. Yes? Okay. So these are all so you will treat your input to be. So typically, when you say polynomial time, you want your solution to be polynomial in the size of the input. Okay, and you treat the number of variables and all the equations as part of your input. In which case, you don't have a bound on the actual solutions in this problem. Okay, if you had a bound, then yes, it is NP or exp or whatever. Okay. Okay. Anyway, so but that's just an aside. Suppose I give you this system instead. Does this system have a solution? It's just a minimal modification of this. You can tell me yes or no. If no, some why? Okay, sure. So is y even or odd based on this? Why? Yeah. So w is 6w is even, 2x squared is even, so y cubed is even. Therefore, y has to be even. What can you say about z? Z has to be even. Why? Because 5x y you just now said was even. So that's even. 6 is even. So z has to be even. Okay, now look at the third equation. Y is even, z is even, 2x is even. What about w squared minus w? Why? Yes, it is w into w minus 1, and that has to be even always. Right? So, but you are saying minus 3 equal to 0. So this can't happen. Right? So this has no solution. Ideally, I should be changing color and saying red and so on here, but it's okay. Yeah, is this clear? So you can look at certain equations and do some analysis and say this has a solution, this doesn't have a solution. Here I was too lazy, so I just gave you the solution. Otherwise, we could have tried to work out what could be a possible solution. And there is no necessity that there should be only one solution. There can be multiple solutions, right? So Hilbert asked, what is Hilbert's 10th problem? Hilbert asks, is there an program or algorithm that will take these the system of equations as input and tell you yes or no based on whether there is a solution or there isn't. Okay, fine. So that is Hilbert's strength problem. So now, as a bad storyteller, I'll already reveal the plot line. So spoiler, there is no algorithm. Huh? Yes, yes. There is no algorithm to check whether a system of I don't know, polynomial equations with integer coefficients has a solution in integers. Okay, so what I'll do in this lecture, however much as it's possible, is to try to give you an idea of how people proved this. Okay, so yes, no, I linear program is linear, right? Here there are all these integer. Ah, right, right. Yeah, when the equations are monomials or whatever, I suppose, right? I don't know when. Uh, these are not linear equations; these are polynomials generally. Okay, like this example here. Okay, if I can properly scroll dependably, I can go back to this. Yeah, like this example here. Okay, these are not linear equations. Okay, anyway, so yes, so this is what we will show in this lecture. So first thing, we can restrict ourselves to algorithms that check for non-negative solutions. Why? In the previous class, Prajakta talked about reductions, etc. So let's just illustrate one reduction here. If there is an algorithm, uh, there is an algorithm to check for integer solutions if and only if to check for non-negative integer solutions. Okay, how? Suppose I'm giving you, let's for simplicity, let's just consider instead of a system of equations, just one equation, some polynomial I'm giving you in variables. Yes. Yes, I'll show how you can make it into one. Let's say you started with one polynomial and you are asking, let's say first you are asking whether, uh, yes, you want to ask whether this has non-negative integer solutions. Okay, how do you reduce it to the general problem? This not all of you might know, so let me just reveal it. If and only if you say that. So when I say this, yeah, so okay, so there is a theorem by Lagrange, right, which says that every positive integer can be obtained as the sum of four squares, right? So uh, and of course the sum of four squares is always positive, right, non-negative. So you can say that if you're given a polynomial equation and you are asking find does this have non-negative integer solutions, instead you can transform that equation to this. Okay, for each variable x1 you introduce four new variables and you instead of x1 you write a1 squared plus b1 squared plus c1 squared plus d1 squared, etc., etc. This second equation has integer solutions if and only if the first equation has non non-negative integer solutions. Okay. On the other hand, uh, you can say that if and only if, oh, sorry, right, if and only if okay. So rather than being verbose, I will henceforth say in Z and in N. By N I mean 0, 1, 2, 3, etc. Okay, non-negative. Right? Because if you want integer solutions, instead you can express each variable x can be expressed as y minus z. Any arbitrary integer is the uh, difference between two non-negative integers. Right? So you can do this. So henceforth we will only look at polynomial equations with integer coefficients, and we will ask for solutions in n, okay, natural numbers. Okay. And this is the problem that we will show has no solution at all. There is no algorithm which will in general solve this. Okay. So another thing, if there is a solution, so like in that earlier example that we had, uh, so here this w equals 1, x equal to 1, y equals 2, z equals 4 is a solution. So if I tell you that a system of equations has a solution, how do you systematically find it? Is there a procedure to find the solution? What is the naivest way in which you can find a solution? Try all values for the variables, right? How do you try? So let's say you want to try the value 0 for w, and 0 for x, 0 for y, and 0 for z, then 1 for z, then 2 for z. You keep on going. You will never, you will never try any other value for y, right? So how do you systematically try all values? There are 4 possible things here. So to make it even simpler, suppose instead of w, x, y, z, I have 2 variables. How do I try all pairs of natural numbers in some sense? Yes, essentially something like that is what is called the Cantor pairing function. Yeah, so you can use the. I can't figure out how to. Oh, okay. Yeah, so what the Cantor pairing function says is it's a bijection between n cross and n. So you want to list all pairs, okay, such that every pair occurs only once and every pair occurs eventually in the list. Okay, so this is how you do it. You do 0 0 and then 0 1 1 0. 0 2 1 1 2 0 0 3, yeah, it's sort of like that. 0 3 1 2 2 1 3 0. Essentially what you're doing is the same idea that he said. First list all pairs where the sum is 0, okay, then list all pairs where the sum is 1, then list all pairs where the sum is 2, etc. But inside each you go by the order of x. Okay, so you see x is 0, x is 1, then x is 2. So commensurately in this second this thing you will have y equals 2, y equals 1, and then y equals 0. Okay, so if you can try to figure out what is the position where xy will occur in, taking 0 to be the first position. Okay, so if you take a general xy, right, before you come to xy you should have first listed all the pairs whose sum is 0, 1, 2, etc., etc., all the way till x plus y minus 1. Right? How many pairs are there with sum k? K plus 1. So to get to xy you will have 1 plus 2 plus dot 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 plus k, because sorry, x plus y, because x plus y is the number of pairs with sum x plus y minus 1. Right? And after that you have to do 0 till x minus 1, which is x many elements. Okay, the value of x grows from 0 till etc., etc. These are all the number of elements before you list x, y, right? And that is the order of this. And this is nothing but okay. So fine. Uh, so this function is called the pairing function. Yeah, it defines a bijection between n cross and pxy is this. So this function is called. So we'll normally denote it with these angled brackets. Okay, and once you can show how to do pairs, you can do triples, quadruples, etc. Okay, so is nothing but x followed by this. Yeah, so you can work it out like this, and you can use this method to actually run through all four tuples of all quadruples of numbers and eventually arrive at the solution for that system. Okay, good. So once so this is the bijection. So there are two inverse maps. Okay, you can think of it as we'll give them names. We'll yeah. So call it LW and RW. Yeah. Yes. So LW is the unique x such that there exists a y with similarly this is okay. So you can do this. So given if you have an algorithm that tells you whether a system has a solution or not, then you can apply this search procedure to actually produce a solution. Okay, good. Okay. So I spent some time on this pairing function and this L and W because these are special functions. Why special? These are what are called Diophantine functions. Okay. So we can talk about Diophantine functions, Diophantine sets, and Diophantine relations. Yes? Somebody had a question? Okay. So what's a Diophantine set? A Diophantine set is a S. A set of natural numbers is Diophantine. If and only if there is a polynomial P with whatever variables, with one distinguished variable x and some other variables, such that S is exactly the set of all numbers x, such that when you plug in that value to the first variable, there exist some values for the y such that px y vector equals 0. Okay. So notice what we are doing here. We are treating x as special. Okay. X is something that will be considered as part of your. So you should think of x as a parameter. Okay. And y etc. are part of your solution. Okay. So think of the y vector as variables and x as parameter. So you fix different values for the parameter. You might have a solution or you might not have a solution. Okay. You pick out only those parameters for which there is a solution. Okay. If S is that, if your set S is exactly the set of all parameters for which there is a solution for this polynomial equation, then you say that that set is Diophantine. Similarly, you will say that what is a relation but just a subset of n to the k, right? So you will say that a relation R, similarly, you will say that R subset of n to the k is Diophantine if there is a polynomial P such that R is exactly the set of all k tuples such that if you plug in these k tuples of values into the polynomial, for exactly these k tuples you will find some solution. For other k tuples you won't find a solution. Okay. Right. And Diophantine functions are exactly those. A function is nothing but a set of tuples with some. What is a function? It's a set of pairs with some specific conditions, right? So, but anyway, let me be explicit. If similarly, I'll just be loose and there exists a P such that okay. So now, one thing I can tell you is that the earlier things that we saw, the function P, L, R, etc., are all Diophantine. Why? Because P x y equal to, so let me not use P. Let me just use the angled bracket notation. So, how do you say this? When does this happen? What is the definition of this angle bracket? X plus y into x plus y plus 1 by 2 plus x, right? So, when would you say that this thing happens? You don't even need to say there exists z, there exists something, etc. It's all the values, all the variables that you need are right here. You just need to say 2z equals x plus y right? When would you say that x equals pw? Sorry, not pw, lw. If and only if there exists y such that the same thing as above. Okay, 2w equals, oh, maybe just to okay. Array. Okay, just to be uniform, and y equals rz. Yeah, the same equation you write. Except in one case you quantify over. In one case the parameter is x and the variable is y. In the other case the parameter is y and the variable is x. Is it clear so far? So I'm just doing some very simple things. I'm introducing a lot of notions, but I'm nothing is. It's all quite elementary, right? Okay. So now somebody said that you can you can sort of compress a system of equations into one equation, right? And yes, and formally you can state it by saying that Diophantine, let's say Diophantine sets and relations okay. So given two relations you can take the conjunction of the two relations and the disjunction of the two relations. Either this holds or, so in the last lecture project I was talking about or and etc, right? So which she was talking about some x or y etc, but you can generalize it. You can say some x loves y or y loves z. So you can do things like that. Okay, so you can combine relations using and or, just like you can combine sets using intersection and union. So do you want to take it as a can you tell me suppose I have two polynomials p and q with the same parameters, yeah? So can you tell me, can you give me one equation that captures both this? Very nice, right? You want P to be 0 as well as Q to be 0, right? And one equation that forces it is to say that P squared plus Q squared equal to 0, right? Because P squared has to be non-negative. We are talking about non-negative solutions, right? So P squared will be non-negative, Q squared will also be non-negative, and if that is 0, then it has to be the case that both P squared and Q squared are equal to 0, which means that P and Q are equal to 0, right? So you can say if and only if there exists y hat and y vector and z vector such that P squared very nice. What about R? This holds R, that holds. So that's one result. Exactly. Right? So you can bring it all down to one equation, okay, system of equations. Now the important question is what, so it's closed under AND, it's closed under OR, okay. When you look at these are called Boolean operators. One other important Boolean operator is not, okay. So you say that not A holds if and only if A does not hold. For instance, you might say your relation could be that of being a prime. So, or let's say x divides y is your relation, then you want to say x does not divide y. Okay. So let's look at that. So let's look at some example. So one question is, we know that if two relations are diophantine, then their conjunction and disjunction are also diophantine. Now, if a relation is diophantine, is its negation diophantine? Is the question. Okay. The answer is no, which you will eventually see. I'll show you. I'll see how much I can show that to you. But it is not closed under negation, and I can give you some intuition. Okay, so let's start with another question. Is okay, so it's a little more technical. We'll come to that in a bit. Okay, so for now, let's look at some example diophantine sets / relations / functions. Okay, so let's start with something simple. X divides y. How do you express it as a diophantine equation? Polynomial, etc., etc. Huh? Y is exactly. So this happens if and only if there exists z such that y is xz. Okay, good. Yeah. How do you say that x is not x does not divide y? But you can't say that it does not exist. This is the whole point. Yes, but I can't say that because I want to show that this is diophantine. Meaning, I want, can I exist as, can I express it as there exists something, something, something? Huh? Plus constant, but that constant should be the remainder. So can you exactly something like that you can say. So you can say, for instance, that there exists a quotient and a remainder such that y equals sorry, I should say, yeah, y equals x times quotient plus remainder, and so I know that I can always do and, okay, and 0 less than or equal to r. No, I shouldn't say 0 less than or equal to r. 0 strictly less than r. But now you should ask, can I 0 strictly less than r, strictly less than x? No, x. Is it clear? I am saying that there is a remainder, a non-zero remainder. But how do I express 0 less than r less than x? So how do I say r less than x? Yeah, if there exists a z such that x equals r plus z plus 1, you have to say, because z is non-negative. So z could be 0 also. So you say z plus 1. Okay, r less than or equal to x, of course you can say by saying there exists z such that x is equal to r plus z. Okay, sure. So what else? For instance, you can say, how do you say, mm, how do you say x is not a prime? Yeah. So there exists y z such that either no y plus 2 times z plus 2 equals x, right? Because you want to say, is it clear? How do you say x is a prime? Normally you would say x divides, sorry, some z divides x implies z equals 1 or uh, z equal to x. Is this a legitimate definition? We have not yet shown how you can do this implies in this thing. So implies is implicitly has a negation, so you can't really do that. Okay, you can, for instance, say that we have already shown how you can say x does not divide y. So one thing you can try to say is, let me, yes, this will delete it. For all x less than, sorry, for all y less, strictly less than x, yeah, you can say either y equals 1 or y does not divide x. Okay, but again there is something that I've sneaked in. How do I say for all y less than x? Right? Okay, so you can't directly say it. In fact, okay, so people who are trying to solve the Hilbert strength problem, one, so we'll see why they had to express lots of things, show that lots of things are Diophantine, and in trying to show this, they want, you already know that Diophantine sets are closed under and they are closed under R. It was very important for them to show that it is closed under this kind of for all y less than x. Okay, the technical name for it is called bounded universal quantifier. Okay, universal quantifier means for all. For all means universal. Bounded because you are saying for all y less than x, rather than saying for every y whatsoever, saying for every y from 0 till this number. So there is a bound. Okay, so one of the important questions people wanted to solve was to show that these Diophantine sets are closed under bounded universal quantification. Okay, I will not actually show that. Okay, we'll assume that and show what the overall result is. But if time permits, I will show you one key ingredient into what goes there. And time will certainly not permit because it's already 4:25. I'm sorry about that. Okay. Um, okay, fine. So here is another important Diophantine thing. This is due to another major figure in logic and computer science and the origins of logic and computer science. Okay, he, how many of you have heard of Gödel? Okay, many of you. So he proved fundamental results in logic. Okay, but uh, very deep results. In trying to prove one of the results, he actually came up with one technical device which is very, very useful across many uh, in lots of domains, in especially related to computability and so on. So he defined what is called a, so this is the theorem by Gödel. There is a Diophantine function beta such that yeah, so there is a function beta which sorts of codes up all sequences. So till now, earlier we saw how to code up pairs. Okay, given a pair, you can write the pair, you can apply the pair function, you get a single number. So what Gödel wanted to do was can I get a single number for any finite sequence where I don't specify the length of the sequence? Okay, because earlier if you looked at the pairing function, for two numbers you have one function. If you want to code up three numbers, you apply pair of pairs or whatever. So for each, if you want to code up four numbers, you have a different function. But what Gödel wanted was one function which codes up all finite sequences. Okay, in the following sense. Okay, this is a function? How can a function code up a finite sequence? In this sense, you give me any sequence of any length, I can find a single number. Okay, u. This u will help you recover all the numbers in the sequence. Okay, via the function beta. Okay, the function beta is very simple. We'll come to it in a minute. Such that beta of ui equals the ith member of the sequence for all I less than or equal to for all I less than n. Okay, this is a very key technical lemma that he proved in his famous paper, which is used all over the place by everyone. Right? I'll not prove this, but I'll give you an example. What is the function beta? The function beta itself is basically what the function beta does is it tries to find the remainder of one number with respect to another number. Okay, so treat u as a pair. Okay, then it has a first part and it has a left part and it has a right part. So beta is basically this. Beta of ui is nothing but the left part of u. Okay, sorry, I should say the remainder that you get if you divide the left part of u by okay. So don't worry about why it is 1 plus 1 plus I, etc. It's 1 plus I because you're talking about non-negative numbers. So I could be 0, right? And that 1 plus, it's all meant to get some a sequence of pairwise relatively primes and then applying Chinese remainder theorem. Some of you might have seen Chinese remainder theorem. If you have not seen, it doesn't matter. So what Gödel proves is that you can always find, for any sequence, you can find a number that codes the sequence through this very simple function. Okay. So tell me why this function is Diophantine. So the beta is supposed to be Diophantine. So why is it Diophantine? Remainder when you divide x by y. How do you express that? Remainder when you divide x by y is r, I want to say. This happens if and only if there exists a k such that yk plus r equals x and 0 is less than or equal to r less than y. Right? So this tells you that r is the remainder that you get when you divide x by y. Okay, so this is Diophantine because we have shown that less than or equal to is Diophantine and is Diophantine, etc. Okay, yes. No, the beta doesn't depend on the sequence at all. You see, because I say there exists a beta. The beta is just this fixed one. Okay. For any sequence that you give me, not countable, for any finite sequence you give me, I'll code it up with a single number. Okay. Of course, I don't have the ability to work with large numbers, so I just tried to work out an example. If you consider the sequence 1, 1, 2, let us say, it's a sequence of length 3, then you can actually verify once you get home that the number 1275, okay, is equals okay. So therefore, what is the number u for this sequence 112? It is not a unique u. You can find multiple u's. One particular u that works is, remember that you have to do 1275, 6. Because 7 is 1 plus 0 plus 1 into 6. Okay, because that's what I have written, right? 1 plus I into Ri. Okay, and 13 is 1 plus 1 into 6. Right? 19 is 1 plus 2 plus 1 into 6. Okay. So, so it fits. So the number that you're looking for is the pair 1275, 6, which of course means 1275 whatever 1281 into 1282 divided by 2 plus 1275 or whatever. So you have to figure that out. Okay. So you see that even for this small sequence, it's a large number, but Gödel gives you a proof which ensures you that you can always find a U that codes this up. Okay. Good. So now that I have shown this, okay. What is the overall strategy for showing that the Hilbert strength problem is unsolvable? So that's what you have to come to. So strategy for the proof of okay. There are several steps. I'll do these steps in some order. First step is to show that okay, what do I mean by a computable function here? Take some informal definition. So think of any programming language you think of, some C, let us say. It could even be a very simple programming language, and you just want to, can I write a program such that if you let the computer run forever, I mean not forever, without any bounds on time or space, if you give it input x, it will produce output f of x. Okay, if that happens, then you say that f is computable, right? So basically, computable functions are all those functions for which you can write a program. Okay, so think of it that way. So you can actually show that everything that is computable, you can. This is a very hard step. Okay, but at least I want to give you an overall idea of how this thing goes. Okay, 2. Enumerate all Diophantine sets as D0, D1, D2, etc. Okay. You can say that, okay, I can always enumerate because what is involved in a Diophantine set, I just need a polynomial equation. Polynomial equations only involve some finitely many variables, and so you can actually enumerate all the equations. Okay, it's countable, etc. You can say that, or you can have a very concrete kind of presentation. Let me just give a concrete enumeration because this will be useful in the next thing. So first enumerate all polynomials like this. So we have Professor Manoj Kumini here. This kind of 3i plus 1, 3i plus 2, 3i plus 3 is a favorite of his. But okay, so first assume that you have variables x0, x1, x2, x3, etc. So you've listed variables in that order. Then this is a very, very concrete kind of enumeration. Okay, you listed out all polynomials like this. Okay, you can convince yourself that all polynomials will be appearing as pi for some I, but only polynomials with positive coefficients. Okay, because there is nothing negative happening here. Okay, I start with a constant 1, then I have xi's I bring in at every 3i step, 3i plus first step, and then I add, multiply, etc. You can convince yourself that every polynomial with only positive coefficients can be found somewhere in this list. And finally, what you want to say is that the set, so now if you have an arbitrary Diophantine equation like this, you can write it, you can transform it as where Q and R have only positive coefficients. This is trivial, right? You just switch sides whenever you see a negative coefficient. And I just told you that Q and R, any Q that has only positive coefficients will appear in that list somewhere. Okay, so there is an I and a J. Okay, now P is represented by what? P will be represented by the number n, which is given by the pair ij. Yeah, so you have the pairing function, right? Apply the pairing function on ij. Okay, you will get this. And how do you represent P? You will represent it as, of course, Pi of x equals Qi of x, Pi of x equals Pj of x. Okay, so this is our numbering. So in general, dn. So remember that we want to enumerate the Diophantine sets. Okay, dn is the set of all x naught such that P left function applied on n equals P right function applied on n. This is a very, very concrete kind of representation. Okay, why am I showing you this? Because of the next thing, right? If you can do such a thing, then you can show that. So is this clear? How I am listing out all the Diophantine sets? The very concrete enumeration of this. If you can do this, then you can. So what I am going towards is, remember in the last class project I told you that there is some diagonal argument which will show that something is not that halting or whatever, something is not computable. I'm actually going to show you the diagonal argument in full detail. Okay, so now I've shown you how to a very concrete way of enumerating all the Diophantine sets. Now, if I can do this, then consider the binary relation U given as follows. Set of all pairs n comma x such that x belongs to Dn. Yeah, so this can be thought of as a universal relation, because for any pair of numbers it tells you whether x belongs. So for any Diophantine set and any number, this U will sort of decide whether x belongs to that set or not. Okay, the nice fact is that this is Diophantine. Okay, and yes. Yes, if it is no, if it is Diophantine, it is not necessarily computable, right? So if it is a Diophantine function, it is computable. But if it is a Diophantine set, okay, you can list out all its members, all the elements of the set, but you can't say whether some number is not in the set. Okay, this is really the problem. Okay, we'll come to that in a minute. So this is Diophantine. I can actually sit and prove this. So just to show you that this whole process is about some kind of programming, programming using equations. Okay, of course, assuming lots of things, because I can't give you all the detailed number theoretic things, which is in itself beautiful. But in any case, so I'll at least tell you what ingredients are involved in this. Okay, so x belongs to Dn if and only if, right? So you want to basically say that there is a sequence of Diophantine sets, right? That so x belongs to Dn. So Dn is a Diophantine set. If it's a Diophantine set, then you should have somehow followed this earlier construction, right? This that enumeration that I gave. So you can sort of capture that enumeration by saying this: if and only if there is U such that, and this is a sequence, right? So there is a sequence of sets that you have built, and there you have to use the Gödel's beta function. There is a U such that, so this captures the first element for you. The second element is actually x. Okay, x naught is what you want to do. So 3i plus 1 is x. 3i plus 1 is xi. So P of 1 is just x naught. Okay, so that's what you're saying. And for all I less than or equal to n, you just write it out. But the point is, you have to show that these Diophantine sets are closed under bounded universal quantification, which is real hard work and which involves a lot of number theory. And poor Manoj can't see it. I can tell you later. It uses what is called the Brahmagupta's equation. Okay, Uh, yeah. So I'll just leave it at that. The 3 coming from, because the 3 is coming in because of this. You are basically saying these are all, so beta u I represents the polynomial pi. Okay, not the polynomial pi, but the polynomial pi whose value is evaluated at this particular x. Okay, that's what you're saying. And some other parameters for some values. So you fixed a value for each variable such that the polynomial pi evaluated at those values is beta of u comma I. Okay, that's what you're saying. Finally, you have to say that so the polynomial of the on the left hand side evaluated should be equal to the polynomial on the right hand side, because remember that your dn is the set of all x naught such that you can find some values such that p ln is equal to p rn. So that is what you are expressing here. Okay, so right, so you see that you want to show that there is no algorithm for solving Diophantine equations, and the way to do it is to actually treat these Diophantine equations as a programming language. Okay, so to express these kinds of things. Okay, in fact, if you can somehow show that this bounded universal quantifier can itself be subsumed under these Diophantine equations, then you even have a universal computer in some sense. This u is a universal binary relation. Okay, for every x and n, it tells you whether x belongs to the nth Diophantine set. Now that you have this final. We already said the Cantor pairing function. So that was like if you think of writing a grid of numbers, that function started here and then it went here, etc. So these were the, I don't know, cross diagonals, anti diagonals, whatever. But there is also a Cantor's diagonal argument, right? How many of you are aware of Cantor's diagonalization? Right? So, which considers this diagonal. Okay, that is the actual diagonal. And then it flips the value in some sense. Okay, we'll see that. Okay, what we'll see now is Cantor's diagonal argument. V, the set V equals all n such that n does not belong to Dn is yeah, so that's the result. So can somebody, this is an argument that anyone can do. So do you want to try? What's your name you said? Yes. Huh? Sai. Yes, okay. You want to try? So you have to do a contradiction. Suppose V is Diophantine, then what do you do? No, if V is Diophantine, suppose V is Diophantine, remember what did we have? We had a very explicit, so V has to be dk for some k, right? Because that was a listing of all Diophantine sets. Okay, is it clear? Recall here that this d0, d1, d2, etc. is an enumeration of all Diophantine sets in a very explicit manner. I had to be explicit because I wanted to show you that this U itself is Diophantine. Okay, but in any case, so suppose V is Diophantine, then what can you say? But now what can you say? Look at the definition of V. V says all n such that n does not belong to Dn. Okay, so now k belongs to dk if and only if dk is the same as V, right? So you can write k belongs to V. But what is the definition of V? All n such that n does not belong to it. N does not belong to Dn. So what will you write here? K belongs to V if and only if K doesn't belong to Dk. Okay, and that's a contradiction. If you have not seen this kind of argument before, this is a very one of the beautiful arguments in mathematics. Okay, first used to show that the set of all real numbers cannot be put in bijective correspondence with the set of all natural numbers. Okay, so you cannot map every real number to a natural number. Okay. Anyway, so this V is not definite. So finally we have all the ingredients to show that Hilbert strength problem does not have an algorithmic solution. So let me at least show you that, and the rest of the details I'll just mention the rest of the details. So there is no algorithm to solve, I don't know. Okay, suppose there is an algorithm. Okay, what will this algorithm do? It will, you give it any polynomial equation, it will tell you whether there is a solution or not, right? In particular, if there is such an algorithm, one second. So this V I have shown is not Diophantine, but earlier I said that, of course I didn't have time to prove it, but it's okay. Every computable function is Diophantine, I said, and that V is not Diophantine. Therefore, what can you conclude? It is not computable, right? So that's a concrete example of a function. So in the earlier lecture you were shown things that are potentially very hard to compute. SAT, for instance. But here is a set that is, this is a function that is impossible to compute. What is the function? I will give you n and you should tell me yes if n belongs to V, you should tell me no if n does not belong to V. Okay, that is the function. That function, it is impossible to compute by an algorithm. Okay. Okay, so final step. Sorry for going over time. If there is an algorithm, what is PU? Remember I said that U is Diophantine, right? The universal set, right? So PU, if it's Diophantine, it means there should be a polynomial, right? So PU is that particular polynomial. Okay. So in fact, you can actually sit and figure out what is the exact polynomial for that. Okay. Apply it on PU. Okay. And so let me be very precise. Sorry. Sorry, just a minute. We can decide V as follows. Yeah. What does it mean to decide V? I should give you an algorithm that if you give me an n, it will tell you yes if n belongs to V, it will tell you no if n does not belong to V. Yeah. Apply the algorithm on PU, NN, PU, NN, and then whatever. The rest of the variables. Let's say the rest of the variables are some y1 to ym. Yeah, recall that PU is the Diophantine equation corresponding to the universal set. Okay, and you are asking whether there is a solution for when you fix the first two parameters to be n and n. Okay, this will happen if and only if n belongs to Dn, right? So you will get a yes or no answer because this is an algorithm which checks whether there is a solution for any given equation. So if the answer to this is yes, output no. If answer is no, yeah, so that's a contradiction because earlier I said that V is not computable. No, I have actually shown that V is computable. Okay, if there is an algorithm to solve for Diophantine equations, solve for integer solutions. Okay, so yes, so this at least gives you an overall proof. Okay, this is a very natural problem. Okay, it is not some contrived problem that has to do with some actual, some model of computation, some, something to do with this. But equations are things that are familiar to you from very early in your school curriculum, right? So these are very simple things, and you see that there are some deep. In fact, I have not been able to show you the various subtleties. And one of the main things is this showing that these things are closed under these bounded universal quantification, and this use of this beta function plays a role even in this part where you say that every computable function is Diophantine, to show that for loops and while loops can be simulated using these equations, you have to use the beta function. Okay, but yes, so I've given you the references, so maybe you can take a look at those and uh, have more fun on your own. Okay, thanks. If there are any questions, I'm willing to answer. Thank you. Yes, yes. There exists such a function for what? Yeah. It is fine. You can say there exists such a function, but you need to display such a function. Okay, how do you? So in this case, the simplest way to show that there is such a function, because you are also saying that there is a Diophantine function, like that, for which you have to display some equations. Okay. Sometimes it is okay to say there exists such a function and go on, but in this case, you want to claim something more, and it so happens that this is a very simple function. Okay, but your question is right. The u that I talked about in this lemma, right? So I said that this 1275. Okay, I was able to work it out for this simple example, but there is no requirement for you to actually produce that u. Okay, it's a very complicated u. So it suffices to say there exists a u. Okay, it is not needed. Yes, someone else had a question. Yes. The references for all this is these two. There is one article, and there is no way to go up quickly. There is a book and an article. The book is called Hilbert's Strength Problem. The article is also called Hilbert's Strength Problem. I've this is like, yes. So these are the two references. Yeah. So you can, yes. Anyone else? So sorry, I've gone over time. I'll stop now. Yes. Okay.